me, we have R is equal to 12 times. Okay, so for each group, we're going to do this particular calculation effectively. Okay, so for each group, we're going to do this calculation. So the first group, let me just bring this back across here. Okay, so the first group, uh, its sum of ranks is 15, which needs to be squared. So it's 15 to be squared all over the sample size, which is 4. Okay, plus for the next group, its sum of ranks is 32, which needs to be squared, divided by the sample size, which is 4, plus for the next group, uh, its sum of ranks is 44, which needs to be squared, divided by 5 this time. So now we have its 44, which needs to be squared, divided by 5. Okay. So that gives us this piece here, which needs to be divided by n, which is the total number of observations. We've already done that calculation. So we know that n, the total number of observations, which is the sum of the sample sizes, is equal to 13. So what we have is that's equal to n, which is 13 times 13 to be squared. So 13 to be squared minus 1. And we're going to subtract from that 3 times 13 plus 1 divided by 13 minus 1. And it's the square root of that. I mean, the formula looks very, very complicated looking, but the maths is very, very simple. It's just boiling down to some additions and divisions and a couple of squares and subtractions. Okay? So now what we end up with is RMR. The correlation for the multichotomous nominal variable against the ranked variable is equal to this particular value here. So let's actually just calculate these individual values. So this is 15. Oh, this is 15 squared divided by 4 gives us a value of 56.25. So it's equal to 12 times 56.25 plus this value here, 42 squared divided by 4 gives us a value of 256 plus 44 to be squared divided by 5 gives us a value of 387.2, okay, which needs to be divided by 13 times 13 squared minus 1. So 13 squared is 169 minus 1 is 168 multiplied by 13 gives us a value of 2,184. And what we take away from that is, well, this is 3 times 13 plus 1, 3 times 14. So 3 times 14 gives us 42, which needs to be divided by 12, which gives us a value of 3.5. And once again, just keep in mind that it's the square root. It's the square root of that value. So let's actually just do this whole calculation here now. So it's 12 times 56.25 plus 256 plus 387.2, and that needs to be divided by 22184, which gives us a value of about 3.84. So this now becomes, let's say, or is 3.84 minus 3.5, which needs to be, it's the square root of that. Okay, so what does that give us? That gives us, we have to get the square root of 0.34. So that gives us a value of the square root of 0.34 is approximately equal to 0.58. It's approximately equal to 0.58. So once again, from a correlation perspective, we can actually see that there is a strong correlation. Don't forget, an R value, let's say less than 0.2 is weak. An R value that's less than 0.5 but greater than 0.2 is moderate. And an R value greater than 0.5 is strong. So what we're saying here is that there's a strong association. Don't forget, this is always going to be positive. Yeah. Okay. So in relation to a nominal variable, it doesn't tell us anything in relation to directionality of the correlation. Okay? It just tells us the strength of correlation or strength of association between the multichotomous nominal variable versus the ranked ordinal variable. So in this particular situation, in this case here, our calculation has shown that there's a strong association between the role of the individual within an organization and their score on some sort of ranking test, if that makes sense. Okay, guys. Once again, this was Jonathan Lambert with Maths and Stats. And I hope that this video was in some way intuitive. And more importantly, I hope that was helpful for you. And thanks for watching. Okay, bye-bye.